Hi friends, before I going to give my lecture, I would like to introduce myself. My name is Pradeep Dandugala. I came from Telangana Tribal Welfare Residential Degree College, Karimnagar. Now I am pursuing B.SC MPC second year in my respected college. Today our topic is binary trees. Let's start our class. It is essential to know about the data structure before knowing about tree. In this class, I wanted to cover the contents are what is tree, what is binary tree, what is binary search tree and operations of binary search tree, tree traversals, advantages and real-time applications of binary search tree. Data structure. Data structure is a specialized format used for arranging, organizing, retrieving, processing and storing the data, or simply in which format we are going to store the data is known as data structure. There are several basic and advanced data structures, all are designed to store the data. Data structures are almost used in every aspect of computer science, is that compiler designing, operating systems, graphics and artificial intelligence. This data structure is broadly classified into two subtypes. The first one is linear structure and second one is non-linear data structure. Now coming to the linear data structure. A data structure in which we are storing the data elements in sequential manner is known as linear data structure, or in which data structure we are store the data elements linearly, that data structure we call like as a linear data structure. Array, stack, queue and linked list are the best examples for linear data structure. Next one, non-linear data structure. A non-linear data structure, it is also a data structure in which we are store the data elements in non-sequential manner. Means in non-linear data structure we store the data elements randomly. Graphs and trees are the best examples for non-linear data structure. Tree. A tree is nothing but it is a non-linear data structure. Why? Because in a tree we store the data elements in non-sequential manner. Means that in a tree we store the data elements randomly. And also a tree is a hierarchical data structure. Hierarchical data structure means that items are logically or internally related to each other in a parent-child relationship in an oral tree. And simply a tree is a collection of nodes and edges. A node is nothing but in this we store the actual data. See one example here. Here it is a normal tree with the data elements of 1, 2, 4, 6, 3, 8 and 7. These are the data elements which this tree has. Now coming to the root node. Root node is a node, it is a tree starting node, or a root node will be always exist at 0 level of the tree. The nodes are connected by edges in a tree, so a edge is a connection bridge between two individual nodes. A edge is also known as link because of a link is the linkage between two separate nodes. Leaf nodes. In a tree we have leaf nodes. These leaf nodes are existing at the ending of the tree, or a node with no child we known as a leaf node. Internal nodes. Internal nodes are the intermediate between root node and leaf nodes, or internal nodes are existing in the middle of the tree. In a tree is also categorized into levels. The root node will be always said to be at the 0 level, and the children of the root node will be said to at level 1. The children of the node at level 1 will be at level 2. So similarly up to n levels the tree is categorized into level wise. Now next one, in a tree we have also height of the tree and depth of the tree. The number of edges from leaf node to root node is known as height of the tree. In this tree, the height of the leaf node is 0. Why? Because the leaf nodes are existing at the ending of the tree. Depth of the tree, the number of edges from root node to that particular node is known as depth of the tree. In this tree, the depth of root node will be 0 because of the root node will always existing at level 0. Types of trees. In tree, we had some types. Now coming to the general tree. General tree is a tree, but in this tree each and every node can contains any number of children. Each and every node can contains any number of children. See one example tree on the screen. Here it is a tree. This tree root node is 1. This root node can contains 3 children. And so in a tree or in a general tree, each and every node can contains any number of children. Next tree is binary tree. Binary tree is also a tree in which each and every node can contains at most 2 children only. Each and every node can contains at most 2 children only. See examples here. 15 is a binary tree. Why? Because this tree root node 15, it does not contains any number of children. So that's why it is a binary tree. And see next example tree, that is 15, 30. Here in a tree, it is a 15 is a root node, 30 is a child node of root node 15. This is a binary tree. Why? Because this root node 15 can contains only one child. So from the definition of binary tree, a binary tree is a tree, it either contains 0 child or 1 child or 2 children, but it neither contains more than 2 children. So see next tree, 15, 30, 20. This is also a binary tree. Why? Because this tree root node 15 can contains at most 2 children. So that's why it is also a binary tree. And last tree, it is not a binary tree. Why? Because this node, parent node, can contains more than 2 children. So this is not a binary tree. And next tree is binary search tree. Binary search tree is also a binary tree. Why? Because it will be also each and every parent node or node can contains at most 2 children. But the main difference between binary tree and binary search tree is binary search tree, its root node can contains higher values when compared to its left subtree, and its right subtree contains higher values than this root node, and its left subtree contains lower values than compared to its root node. So we had some operations on binary search tree. That operations are creation operation, insertion operation, deletion operation, and searching operation. These are the 4 operations which we performed on binary search tree. Now let's see that operations one by one. So here it is a creation operation in a binary search tree. In creation operation, we create a binary search tree with some elements. Here we have one example. We have some data elements 45, 17, 45, 15, 79, 90 and 10. These are the data elements which we had. So to create a binary search tree, take the first element as a root node. Now I take the first element root 45 as a root node and take the remaining elements one by one by following the binary search tree rules. Now I take the next data element 15 and compare this element 15 with the 45. 15 is less than 45, then I go to its left side, and I take the next element 79. I compare the element 79 with root node 45. 79 is greater than the 45, then I go to its right side, then I place the element 79 at that place. Now I take the element 90 and I compare the element 90 with its root node 45. 90 is greater than the 45, then I go to right side and I compare the element 90 with 79. 90 is greater than the 79 and I place the element 90 at that particular place. Sorry, here we have a element 79, but we have example 79. We place that 75 with 79. Insertion operation. In insertion operation, we insert a new element into a binary search tree, already existing binary search tree. Here we have one example. It is a binary search tree with the data elements are 100, 20, 500, 10 and 30. These are the data elements. So into this binary search tree I wanted to insert the data element 40. So I compare the data element 40 with the root node 100. The data element 40 is must be less than root node 100. So now go to left side, and again there is a element 20. I compare the element 20 with the 40. 40 is must be greater than the 20. Now I go to right side, and again there is a element 30. I compare the element 40 with 30. 40 is must be greater than 30. So now I go to its right side, and there is no element to compare. So I place the element 40 at that place. So this is the insertion operation which we performed on binary search tree. Now next, searching operation. In searching operation, it is used to search for a particular element in already existing binary search tree. Here we had one example. See this example. Here I tried to search for a element 9 in this already existing binary search tree. First I took the element 9 and I compared the element 9 with 15. 9 is must be less than 15. So now I go to its left side, and again there is a element 6. I compare the element 9 with 6. 9 is must be greater than 6. Now I go to its right side, and again there is a element 7. And again compare the element 9 with 7. 9 is must be greater than the 7. So now I go to its right side, and again there is a element 13. I compare the element 9 with 13. 9 is less than 13. So I go to its left side. Yes, of course there is a element 9, we found it. So this is the searching operation which we performed on binary search tree. By using this searching operation in binary search tree, we reduce the half of the searching time. The searching is very easy. This is the main advantage of searching operation which we had on binary search tree. And next operation is deletion operation. In binary search tree we are also have deletion operation. In deletion operation we delete some particular elements from binary search tree. But this deletion operation which we perform in 3 ways. The first way is deleting a node with no child, means that deleting a leaf node. And second way is deleting a node with one child, means that deleting a node with one child. And third way is deleting a node with two child. So these are the 3 ways of deletion operation. Now let us see first operation or first way of deletion operation. In first way we deleting a node with no child, means that leaf node. So here we had one example. In this example I wanted to delete the element 85 from this binary search tree. So while we deleting a node with no child is very easy. Why? Because a node with no child is a leaf node. These leaf nodes are always existing at the end of the tree. So it is very easy to be delete a data element 85. This is the first way. And coming to the second one, delete a node with one child. Delete a node with one child, it is a second deletion method. While we deleting a node with one child, we must be replace that node with its child node. With its child node. See the example here. Here in this example I wanted to data element 12. So while we deleting this data element 12, we must be replace the data element with its child node. Why? Because we can't replacement this node with its child node. The relation between this child node and parent node of its node 12 will be lost. The relation between data element 6 and data element 25 will be lost. So while we deleting a node with one child, we must be replace the data element with its child node. So see left side. Here we replace the deleting element with its child node. So 6 will be at 12th place, 12 will be at 6th place. So 12 will be here, it is a leaf node. Why? Because this 12 does not contains any number of child. So we easily delete this element 12. This is the second way of deletion operation. Now coming to the third way. In third way, we delete a node with 2 child. We delete a node with 2 child. While we deleting a node with 2 child, we must be replace that node with its in-order successor or in-order predecessor. In-order successor means that it is the minimum value of its right subtree. In-order predecessor means is the higher value of its left subtree. Why? Because a binary search tree is a binary tree in which its left subtree can contains less values than when compared to root node, and its right subtree contains higher values than the root node. So while we deleting a node with 2 children, we must be replace that node with its left subtree higher value or right subtree lower value. So here see one example which we had on the screen. In this example, I wanted to delete a node 15. So while we deleting a node 50, I replace that node with in-order successor. In-order successor means it is the less value of its right subtree. So see here 50 is the less value which we has on its right subtree. So we must be replace the data element 52 with its in-order successor. This is the deletion third method. We had some traversal methods on binary search tree. Binary search tree provides mainly 6 types of traversals, but these traversals are essential and important traversals. Traversals means that it is a process of visiting each and every node of a binary search tree. It is a process of visiting each and every node of a binary search tree. Here we have the 3 types of traversals: in-order traversal, pre-order traversal, post-order traversal. Pre-order traversal follows the NLR method. N means root node, L means left node, R means right node. In pre-order traversal, we had one example here with the data elements of 5, 3, 8. It is a binary search tree. Why? Because this parent node can contains at most 2 children, and this binary search tree, its left node must be less than the root node and its right node is greater than when compared to root node. So it is a binary search tree. In this tree, we perform a pre-order traversal. Pre-order traversal means that in this we visiting the root node first. First we visit the root node 5, then after we visit the its left node, that is 3, and then after we visit its right node, that is 8. So we have the order of data elements, that is 5, 3, 8. And coming to the next traversal method, in-order traversal. In-order traversal, it is also one type of traversing method. It is used to traversing or visiting each and every node of a binary search tree. So in this example, first we visiting the left node. Why? Because it follows the LNR method. L means left node, N means root node, R means right node. So in this traversal we visit the left node first, then after we visit the root node. Why? Because in this traversal we give the second priority to the root node. So we visit the root node second time, then last time or third time we visit the right node. So it's give the 3, 5, 8. This is the order of the data elements. The main advantage of in-order traversing method is it's give the sorted order, while when we do in-order traversal, it's give the sorted order of the elements. It means it gives the ascending order of the data elements. See here 3, 5, 8, this is the ascending order of the data elements. And last but not least, that is traversing method, is post order traversal. In this traversal we visit the left node first, then after we visit the write node, and last we visit the root node. It gives the order of the data elements are 3, 8, 5. These are the traversing methods. Now coming to the advantages of binary search tree. When balanced binary search tree is quick at insertion and deletion operations also. In binary search tree, most of the operations have the time complexity of order of log n. These binary search trees works efficiently when compared to other nonlinear data structures, because these binary search trees are not needed the pointers and other data structures. These binary search trees works efficiently to storing the data. By using the binary search tree, we also perform range queries. Range queries means that it has some pre-processing input data. It has some pre-processing input data. And last advantage is binary search tree eliminates half of the searching time, or we can reduce the half of the searching time by using binary search trees. The searching is very easy by using binary search trees. And coming to the move to the next slide, that is real-time applications of binary search tree. Binary search trees are used to implement Huffman coding algorithm. Huffman coding algorithm means it is a lossless data coding algorithm. It is one kind of algorithm. In this algorithm, we assign the length of the variable to different input characters. This is a Huffman coding algorithm. In this Huffman coding algorithm, we using the binary search trees, and also binary search trees are used in expression evaluation. Expression evaluation means to find out the value of the given arithmetic equation, to find out the value of a given arithmetic equation or expression when a variable is replaced by a number. A variable is replaced by a number. Now coming to the next real-time application is routing algorithms. Routing algorithms. The binary search trees are also to be used in routing algorithms. A routing algorithm is nothing but it is a procedure to transfer the data packets from source to destination. And also binary search trees are used in data caching. Binary search trees are used in data caching. Data caching is a process. Data caching is a process where we can store the data. We can store the multiple copies of data or multiple copies of files in a temporary storage location. Maybe that stored data can be represented in the form of binary search trees. So that's why a binary search trees are also to be used in data caching. And also binary search trees are used in priority queues. A priority queue means that in this queue it is a one kind of queue. In this queue we give some priority to the numbers. This is a priority queue. So these are the real-time applications of binary search trees. Thank you everyone.
Group 1, Group 2